Hello everyone, and welcome to today's webinar titled Hemoglobin A1c, the Hidden Factors, Biological Interferences. My name is David Sachs and I'll be your moderator today. Today's educational webinar is presented by LabRoots and brought to you by Sebia Incorporated. Before we begin, I just want to mention that I would like to encourage the audience to participate by submitting questions at any time during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. There are two speakers today. The first speaker is Dr. John Higgins, an associate professor at Harvard Medical School. His title is The Hidden Factors, Biological Interferences, Red Blood Cell Age. And then when he's finished his talk, I, as a senior investigator at the NIH, will speak. My title is The Impact Factor, Importance of Variant Detection in Hemoglobin A1c Measurement. And at the end of my talk, there'll be time for questions and answers. So without further ado, I'd like to introduce Dr. John Higgins.
Thank you, Dr. Sachs, for the nice introduction. The title of this presentation is The Hidden Factors, Biological Inferences, Red Blood Cell Age. What I'd like to tell you about in the next 20 minutes or so is the effect of red blood cell age on hemoglobin A1c. Let's start just by reminding ourselves why we're measuring A1c in the first place, and that's because A1c tells us about mean glucose variation. You can see from this plot, which was taken from a publication related to the DCCT trial in 2002, that as average glucose increases, A1c increases. So A1c tells us a whole lot about a patient's recent average glucose level. What you can also see, though, is that there's quite a bit of scatter around that regression line. So while the trend is certainly there, increasing average glucose leads to increasing A1c, there's another source of variation that we can't quite explain. If we look at data from another study, the A1c derived average glucose study by David Nathan and colleagues, we can see a similar scatter around the regression line. What the regression line allows us to do is to tell patients with a hemoglobin A1c of 7% that their recent average glucose is about 154 milligrams per deciliter. But if we zoom in on this slide, and we look at the individual measurements for all the patients who had A1c measurements of 7%, we can see that there's actually quite a bit of variation in their average glucose. There's one individual there with the green arrow who had an average glucose of 132, another individual with the yellow arrow who had an average glucose of 186. But yet if A1c is used to guide their treatment, both of them will be treated the same because their A1cs were both 7%. What we'd like to understand is what causes this non-glycemic variation in A1c. And that's the topic of this presentation. So first, I'd like to provide some of the evidence suggesting that red blood cell age variation can alter A1c independent of glucose. And then I'll discuss a few common clinical scenarios where red blood cell age does seem to vary. And lastly, I'll spend most of the time discussing some evidence that suggests that red blood cell age variation may be the dominant source of non-glycemic variation for A1c. And at some point in the future, it might be possible to adjust A1c for red cell age variation and end up with an even more accurate estimate of average glucose using A1c. Well, I'm going to be spending the next little while talking about how we can improve A1c, about its shortcomings. But before I get started, I just want to remind everyone that A1c is actually one of the best clinical tests. Because of the high prevalence of diabetes, with hundreds of millions of people worldwide suffering from diabetes, and the high rates of morbidity and mortality associated with the disease, the fact that A1c has allowed us to improve diagnosis and management of diabetes means that it has reduced morbidity and mortality probably as much as any other lab test we have available. So those figures there are showing the high rates of cardiovascular risk among diabetics, as well as the high rate of retinopathy leading to blindness. And what A1c has enabled us to do is to lower those rates of morbidity. Now, while A1c is a great test, it does have some shortcomings, and there is room for improvement. This recent study from Perlman and colleagues reinforces what we saw on the DCCT plot and the ADAG plot, that while there's clearly a linear trend between increasing mean glucose and increasing A1c, there's also quite a bit of scatter around that regression line, and we're going to make errors when we infer average glucose from A1c. So let's review some of the evidence for a role for RBC age variation. As we said from the beginning, the recent glucose concentration determines A1c, and there's solid evidence that RBC age variation and variation in the mean red cell age, which I've shown here as MRBC, there's strong evidence that MRBC also influences A1c. So we can do that by comparing the effects of increasing glucose and increasing red cell age at the same time. The schematic shows that when glucose is high, following the steep black line, if we wait longer, the A1c will become much more elevated. And when glucose is low, time will continue to have an effect, although the effect is more shallow. There's evidence both in vitro and in vivo for this relationship for effects of both glucose and time on A1c. The in vitro evidence comes from Ladizinski and colleagues, who cultured red blood cells in different concentrations of glucose. The red X's correspond to conditions where glucose was high, and when they allowed the red cells to incubate longer in the solution, the A1c increased, and it increased quite quickly. The blue X's are when the glucose concentration was lower, and the A1c continued to increase, but it did not increase at quite the same rate. Robert Cohn and colleagues found a similar pattern in vivo. They used biotin to label red blood cells, both from diabetic patients and non-diabetic patients. And in the diabetic patients, who would tend to have a higher glucose concentration, we can see that as the mean of the age of the red cells increased, the A1c increased. And similarly for the diabetics, as the mean age of red cells increased, the A1c increased. So these two panels convince us that A1c and glucose independently contribute to A1c variation. There are many other proposed contributions to A1c variation. There's evidence in the literature that iron deficiency is associated with differences in A1c independent of glucose. Anemia as well, patient age, ethnicity, thalassemia carrier status, and hemoglobin variants as well are associated with differences in A1c. What I would like to suggest in the remainder of this presentation is that many of these factors seem to exert their effect by altering the red cell age distribution, by altering the mean red cell age. Some of these effects will persist, for instance, like hemoglobin variants. But for many of these other effects, if we can estimate the mean red cell age accurately, we might be able to adjust A1c for this non-glycemic effect and end up with a much more accurate estimate of average glucose. So next, I'll describe some common clinical scenarios where RBC age appears to vary and have an influence on A1c independent of glucose. There are a number of different scenarios. The few that I'll discuss are listed here. So let's just start first with pregnancy. We know in pregnancy that there are changes in red blood cell production. A recent study by Edelson and colleagues in the Journal of Clinical Endocrinology and Metabolism showed that in a cohort of pregnant women, the average glucose increased from the first trimester of gestation to the second trimester and beyond. and then after birth, the mean glucose decreased. If glucose was the only effect on A1c, we would expect the A1c in this cohort to show the same pattern. But what the investigators found was that the A1c pattern was the opposite. So in the middle point, when the glucose concentration is increased, A1c has actually decreased. This result suggests that the mean red cell age had decreased in pregnant women. And in fact, there's evidence from older studies. Here's one study from Pritchard in anesthesiology a few decades ago, showing that the red cell volume in pregnant women increases by perhaps about 30%. And the idea is that an increased rate of RBC production will lead to a higher fraction of young RBCs in the circulation, and that would correspond to a younger mean red cell age, which would decrease the A1c above and beyond what the increase in glycemia would cause. Another condition that's associated with A1c change is iron deficiency. Here's a study from Diabetes Care in 2010 measuring the effect of iron and erythropoietin treatment on A1c in patients with diabetes and chronic kidney disease. We can see before the iron treatment, the A1c level was 7.4% on average when these individuals were iron deficient. After iron treatment, the A1c went down, went from 7.4 to about 6.96 on average. Now during that time, the hemoglobin level rose from 9.7 to 10.5, suggesting again, as in the pregnant situation, that there might have been an increase in red cell production due to a new supply of iron. Well, when we see that the A1c dropped from 7.4 to 6.96, we might have expected the glucose to rise during that time, to drop during that time, but the mean blood glucose actually increased from 9.5 to 9.7. So glucose goes up, but A1c goes down, similar to what we saw in pregnancy. And given that the hemoglobin level increased, this situation again might be explained by a decrease in mean red cell age associated with increased red cell production. Another condition, or another study also reported a similar pattern for iron deficiency, showing that iron led to an increase in red cell parameters, increase in red cell count parameters, but was associated with a decrease in A1c. And this pattern too would be consistent with the idea that iron deficiency would lead to a decrease in red cell production, and that a response would lead to an independent effect on A1c. Another condition that's been shown to be associated with A1c independent of glucose is G6pd deficiency, or glucose 6-phosphate dehydrogenase deficiency, which is a mild enzyme disorder that can be associated with faster red cell turnover. Wheeler and colleagues showed in a large genetic study that individuals who had a variant, an enzyme variant for G6pd associated with higher red cell turnover, that they tended to have lower A1c. So the leftmost points in the plot correspond to the individuals with this G6pd variant, and you can see that their A1c was lower than for the individuals who did not have that variant. The situation becomes more complicated, however, when Wheeler and colleagues considered the effect of this genetic variant in individuals with different genetic backgrounds. They looked at 22 other genes that were associated with RBC traits and with A1c, but did not have any influence on the risk of developing diabetes. And if we look at those three sets of points in the black boxes, again, the leftmost point in each box corresponds to the individuals with the G6pd deficiency, and they tend to have a lower A1c, but the magnitude of that effect is quite different in the three groups. And these authors suggested that the other genes were modifying the effect. So we can see overall that there may be many more genetic variants and possibly other clinical conditions where red cell age is altered to a degree that will affect hemoglobin A1c. So I'd now like to move on and provide some evidence and rationale for why it's likely that red cell age could be the dominant source of non-glycemic variation in A1c, and suggest that there might be a way to adjust for this variation. And we'll start by considering the relationship between A1c and average glucose in an individual red blood cell. We think about the A1c level, or the glycated hemoglobin fraction, in a single red cell. We can go back a few decades ago to the discovery of the glycation reaction, the chemistry of the glycation reaction, by Frank Bunn and colleagues. What they found was that glucose is added to the amino terminus of one of the beta-globin chains of hemoglobin, and that this reaction is very slow and it is only slightly reversible. It's basically an irreversible reaction. What that means is the chemistry is very simple. There's no enzyme involved. It's a slow reaction. It's not irreversible, and we can then simulate that reaction and estimate its effect using simple models of chemical kinetics. The box shows the chemical reaction of hemoglobin being combined with glucose at a rate quantified by the Kg rate constant to form glycated hemoglobin. This simple chemical reaction can be described mathematically by the equations below. And the equation in the bottom right tells us how to estimate the hemoglobin A1c fraction in a red cell that's T days old. In order to estimate the hemoglobin A1c fraction in a red cell that's T days old, we need to know what glucose that red cell has seen. What is the glucose concentration that red cell has seen over its lifespan? With the advent of continuous glucose monitors, it's possible to get this glucose data and to make this prediction with high accuracy. So given an expression for the hemoglobin A1c in a red cell of age T, then we need to figure out how many red cells are there that are T days old, or T plus 1, or T minus 1, etc. And we do that by considering the full distribution of red cell ages in the population. And I won't go into all the details because the relationship between the population of red cells and A1c is somewhat tricky, but I'll give you a glimpse at what this relationship looks like. One of the reasons it's tricky is because the influence that glucose has is not straightforward on red cells of different ages. If we consider the full distribution of red cells in the circulation for a nominal patient with a red cell age of 100 days, we can think about which glucose concentrations are going to affect which red cells. So if we focus initially on the red cells that are the oldest red cells in the circulation, those that are 100 days old, they've been circulating for 100 days, so they've seen all of the glucose concentrations from the past 100 days. But as we consider the younger cells in the circulation, for instance, the 50-day-old cells, they were not exposed to the glucose prior to 50 days ago. The only glucose that influences their A1c level is the glucose more recently. And if we zoom all the way to the present, to the red cells that were produced in the bone marrow yesterday, the only glucose they've seen is just yesterday's glucose. So what that means is that the effect of glucose on A1c is weighted by time. The older glucoses have much less of an effect on A1c because they're only affecting the A1c in the really old red cells, while the more recent glucose concentrations are affecting A1c in all of the red cells. So given this approach to studying A1c in single red cells, and then integrating the effect of the single red cell A1c over the full population, we can then predict the A1c for an individual if we have an estimate of that person's mean red cell age and we measure the glucose. I won't go into the details of how that's done right now, but I will show you an example of the results. So if we take this data plotted here is from a clinical trial of diabetes patients who had continuous glucose monitoring, which enabled accurate measurement of their average glucose shown on the x-axis, and A1c measured on the y-axis. These same individuals 6 months earlier had another set of measurements which allowed us to estimate their mean red cell age. So if we assume that only glucose and red cell age determine A1c and that nothing else has any influence, we can use the model that I described previously to predict the average glucose. And then we can compare our prediction to what was measured with the continuous glucose monitoring. So in this case, the individuals with low mean red cell age and high mean red cell age would have their A1Cs adjusted to match those that would be expected for someone with a mean red cell age equal to the population mean. When we do that adjustment, as shown on the next slide, you see that the average glucose we estimate from the A1C corresponds much more precisely, is much more accurate compared to the measurement. So the results of this study suggest, at least for this cohort, that mean red cell age and glucose are the only factors significantly influencing hemoglobin A1c. The basic idea here is if hemoglobin A1c is determined only by glucose and by red cell age, then what that means about our current clinical approach is that we're measuring hemoglobin A1c, and then we're assuming that every patient has the same mean red blood cell age equal to the population average. Making that assumption, we're then able to infer the mean glucose. But if we use a method like the one just described, we can measure A1c as before, but we can actually reverse the expression, and we can measure the average glucose using a CGM device, a continuous glucose monitoring device, and then we can use the A1c result and the glucose result to estimate the mean red cell age. And then in the future, we can use that mean red cell age to adjust our interpretation of A1c. So here's how this might glucose monitor for some period of time to measure a glucose time series, measure an A1c, and then we could plug the glucose data and the A1c into this equation and use the model to estimate the patient's mean red blood cell age. Then in the future, when the patient is no longer using a continuous glucose monitor and the patient has an A1c measured, we can then use the model in the reverse direction. So here's what a patient with an A1c of 6 would be told, that their average glucose is about 131. But if this were a patient whose mean red cell age had previously been estimated and was slightly short, we would know from the model that the glucose needed to produce a hemoglobin A1c of 6.1 in this case would correspond to a much higher glucose. We've tried this approach in some public data sets, and we found, for instance, here's an example of a patient who did have a mean red blood cell age estimated at 45 days and an A1c of 8.1%. The standard regression formula would have provided an estimated average glucose of 186, but using the method described here, we estimated that the glucose actually had to be much higher, 209, in order for these young red cells to have become 8.1% glycated. We had independent glucose measurements available that showed that, in fact, this patient's average glucose was 210, much closer to the mean red cell age adjusted A1c than the unadjusted A1c. Over a set of 4 cohorts of subjects, this method appears to be much more accurate than current regression approaches. The results here are comparing the errors in estimated glucose using the current method shown in red and a mean red cell age adjusted method shown in blue. A perfect estimate of average glucose would have an error of 0, shown by the perfect arrow in the black line there at an AG estimation error of 0. Because there's some error in the hemoglobin A1c measurement, in reality, the perfect error is not achievable, and due to analytic error, an error of about 3 is all we could hope to achieve. And we can see that those blue boxes, which represent the performance of the mean red cell age adjusted method, come pretty close to doing as well as we can expect given A1c analytic variation. So this method shows promise for helping us adjust for non-glycemic variation in A1c and producing more accurate estimates of glucose. There are other methods in development different from the one I've described here, and they are promising as well. It's hoped. I'm hopeful that at some point in the near future, patients will be able to benefit from these methods. One last point I want to make, though, is that these methods for improving the accuracy of hemoglobin A1c instead of, as we currently do, instead of assuming what the patient's mean red cell age is, so that's crossed out here, instead of assuming the red cell age, if we measure an A1c initially, we can infer that patient's mean red cell age, and then in the future we can adjust subsequent A1cs for the effect of red cell age and provide a more accurate average glucose. But as we can see from this approach, in order to take advantage of these adjusted A1cs, we'll have to measure A1c twice, once to estimate the mean red cell age, and then in the future when we want to estimate glucose. As a result of these two measurements, the analytic error in A1c becomes even more important to reduce. And it's exciting, as you may have seen in the first presentations from this series, that the accuracy of A1c assays has improved significantly over the last years. This table here is a recent survey published by the NGSP, and it's exciting to see that there are some A1c assays with coefficients of variation that are actually below 1%, which is terrific. Even lower would be better, but this is tremendous improvement. There are other assays with mean biases that are very close to zero, one shown here with a mean bias of 0.03. And then there are some assays which combine very low bias with very low CV. And these performance characteristics are important because, for instance, if the error in the A1c assay were 2%, if the coefficient of variation were 2%, then for a patient with an A1c of 6, the true value of A1c could be anywhere between 5.76 to 6.24. And for an A1c of 7, the true value due to analytic error could be anywhere from 6.72 to 7.28. In the case of an A1c of 7, that potential analytic error would mean that the average glucose estimate could be wrong by 5 or 10 milligrams per deciliter, which, as we've seen previously, is quite significant. So just to sum up what I've discussed, I hope I've shown you, first of all, that RBC age can certainly alter hemoglobin A1c independent of glucose. And secondly, that's important to think about because there are many clinical scenarios where RBC age may be altered. And lastly, I hope I've persuaded you that RBC age variation might be the dominant source of non-glycemic variation in A1c. And maybe sometime in the future, if we can adjust for this non-glycemic variation due to RBC age variation, we'll end up with an even better estimate of average glucose. And A1c, which is already a terrific clinical test, may be even more useful for patients and physicians. Be happy to answer any questions in the question and answer session. Thank you.
Thank you, Dr. Higgins. I'm going to talk about the importance of variant detection in hemoglobin A1c measurement. Now, due to the COVID pandemic, most of us have had some time where we've worked from home, teleworked, and we haven't been able to go to conferences. That's why this is a video conference. And like many of you, I'm sure we're all looking forward to when we can attend a meeting in person. I'm just hoping that I do not end up, when I'm flying to the conference, in a situation like this, where the pilot comes on and says, "This is your pilot speaking, I'm working from home today." So long before there was a global COVID pandemic, there was a global diabetes pandemic. This slide from a paper published in 2005 shows on the vertical axis the years, on the horizontal axis the affected population in millions. In 2005, they estimated there were slightly over 200 million people in the world with diabetes, and the prediction was by 2030 there would be approximately 350 million. So what has happened in the last 16 years since this was published? Well, the latest data from 2019 from the IDF, International Diabetes Federation, and they estimate that in 2019 there were already 463 million people in the world with diabetes, and by 2030 they project 579 million. That's well over 500 million people with diabetes. So with that background in mind, let's talk a little bit about hemoglobin, and just a brief background about hemoglobin. It is made up of 4 globin subunits, and in healthy adults, hemoglobin consists predominantly 97% is hemoglobin A, which has 2 alpha and 2 beta chains. Hemoglobin A2 is about 2.5%, and hemoglobin F, or fetal hemoglobin, is 0.5%. And the difference is they all have alpha chains, but A2 and F have delta and gamma chains respectively. Now, these percentages change, obviously, in the presence of a hemoglobin variant. So to date, the 1,397 hemoglobin variants have been identified, but the most common ones by far are hemoglobin S, C, D, and E. And this slide shows the distribution of the common hemoglobin variants. Thalassemia is shown in green. Hemoglobin S, which is the second most common, is in orange, predominantly in Africa and the Mediterranean region. Then there's hemoglobin C, which is in West Africa, and hemoglobin E in purple, which is predominantly in Asia. Now, because of travel and migration, the actual distribution is a little different. So, for example, shown here is hemoglobin S. The red dots are where hemoglobin S is. And you can see, in addition to Africa, there's a lot of hemoglobin S in North and South America, as well as Europe. Well, now, with that background in mind, let's talk about glycated proteins. And the definition of glycation, it's the non-enzymatic addition of a sugar to amino groups of proteins. And this was first described in the food industry more than 100 years ago by Maillard. And this nice juicy steak, the outside of the steak, beautiful color, is due to glycation. Now, in humans, probably all proteins get glycated, certainly most of them do. But for convenience, since we can easily draw a blood sample, we actually measure glycated hemoglobin. And the analyte measured most frequently in the world is hemoglobin A1c, which is hemoglobin specifically with glucose, shown in pale blue, attached to the N-terminal of the beta chain. And hemoglobin A1c is very, very widely used. I'm just going to briefly go through the main clinical values. It's used to monitor long-term glycemic control. It's used to adjust therapy. If it changes by more than 0.5%, clinicians adjust the patient's treatment. It's used to evaluate new medications for diabetes. It's used now to diagnose diabetes since 2010. And very importantly, it's a measure of the risk for the development of microvascular complications. Just briefly to go into the analytical methods. So it was first identified in 1968 by Samuel Rabar, and then in 1978, assays became commercially available. In 1988, the American Diabetes Association, the ADA, recommended routine monitoring. Currently, there are more than 250 hemoglobin A1c assay methods, but these can be conveniently divided into two general principles. The first is charge difference, so the separation of the glycated from the non-glycated hemoglobin occurs based on differences in charge, and these are capillary electrophoresis and HpA1c. The second principle is differences in structure between the glycated and the non-glycated, and the categories include boronate affinity chromatography, immunoassays, and more recently, enzymatic assays. I'm going to, for the rest of my talk, focus only on the charge differences. So this is the principle of capillary electrophoresis. You have a very narrow capillary that is connected to a positive and negative charge. You have a very high power supply, and the hemoglobin A1c separates from hemoglobin A, and this is seen by a detector. And I'm going to show you examples of a tracing. So this would be a capillary electrophoresis. This is what you would see if you ran one. And you can see hemoglobin A0, which is non-glycated hemoglobin A, is the peak in pink. Hemoglobin A1c is the blue peak here. And there's also hemoglobin A2, which, as I mentioned, is the second most common hemoglobin, which can be separated here. And then the instrument quantifies them, and you can read the percentages of the different peaks. HpA1c is similar. Separation of hemoglobin A0 from hemoglobin A1c, and you quantify the peaks. And the difference being with HpA1c, you can see the baseline's not quite as smooth as capillary electrophoresis, and also there's no hemoglobin A2 separated. So let's talk about the influence of the hemoglobin variant on the hemoglobin A1c result. And I'm going to divide this into two different groups. So if there's a variant, it may interfere with the hemoglobin A1c measurement itself. So this is an analytic interference, happens in the instrument. The patient's hemoglobin A1c reflects their mean glucose. The second category is where the variant may influence interpretation. That means it actually changes the hemoglobin A1c value so that it no longer accurately reflects the mean glucose concentration. So let's talk about briefly the analytic interference. So it's very important to realize that one cannot measure hemoglobin A1c in individuals with homozygous hemoglobin S or C because there's no hemoglobin A. They have two hemoglobin S chains. And so there's no hemoglobin A, obviously there's no hemoglobin A1c. However, one can measure hemoglobin A1c accurately in most heterozygous hemoglobin variants if you use the appropriate assay. And how do you find the appropriate assay? How do you choose? We can get all of that information from the NGSP website. I'm just going to briefly give you an example of what you can find on the NGSP website. What I've shown here, I know this is a very busy slide, but I just want you to get the concept. The left column is the different methods, and then the next four columns are the common heterozygous variants, and this shows whether that variant will interfere with that method. So everything that's in yellow means yes, there's an interference. You shouldn't use that method for that variant. And capillary electrophoresis is shown near the bottom, and you can see none of the common variants interfere. But it's important to be aware that many individuals with these heterozygous variants, such as hemoglobin AS, which is sickle cell trait, AE, thalassemia, etc., have no idea that they have the condition. And you can usually identify these so-called silent variants if you use a separation method based on charge, that is capillary electrophoresis or HbA1c. This shows an example of capillary electrophoresis in an individual heterozygous for hemoglobin S. So you can see the S peak in gray and the A peak, A0, in pink. So you can clearly identify the variant. Now, let's talk about if the variant interferes with interpretation. You've heard a very detailed and very elegant discussion of erythrocyte lifespan. I just want to highlight a couple of points. Any hemoglobin variant that significantly alters the red blood cell lifespan will alter hemoglobin A1c. And that is clearly evident from Dr. Higgins's talk. And in this situation, the hemoglobin A1c value will not accurately reflect the patient's mean or average glycemia. So let's do a simple calculation. Everybody's taught that the red cell lifespan is 120 days, but like most analytes, there's presumably a range in healthy individuals, and actually Dr. Higgins has shown that. So, your sodium's 135 to 145, so there's a range, it's not 140. So let's assume, and I don't know that this is real, but let's assume the red cell lifespan is 120 plus minus 10 days. If the individual has a hemoglobin A1c of 7% with a lifespan of 120 days, if their lifespan were 110 days, the hemoglobin A1c would be 6.4%. Now, this means that the target for treatment of somebody with diabetes is 7%. So the red cell lifespan is 110, the clinician would think this patient is doing very well. Conversely, if the individual has a lifespan of 130 days, the hemoglobin A1c would be 7.6%, and the clinician would increase the therapy in that patient, even though the patient would have the same average glucose concentration as the individual who has 7% with a 120-day lifespan. So it's important to detect atypical hemoglobins. And I'm just going to briefly describe a study that we performed where we evaluated the medical added value of capillary electrophoresis and compared it to immunoassay for hemoglobin A1c measurement. And we determined the prevalence of a variant hemoglobin in this population during routine hemoglobin A1c measurement. And any hemoglobin A1c profile that was flagged as atypical by the phoresis software and the capillary electrophoresis was investigated further. And this study was conducted in February of 2017 at AMPATH Reference Lab in South Africa. A brief overview of the results. There were 2,364 individuals who had hemoglobin A1c measured during that month. This was normal in 92%, and atypical hemoglobins were seen in 187 people, or 8% of the population. The most common abnormality was decreased hemoglobin A2, and this can be seen clearly in this tracing here. This was identified in 145 people, or 6.1% of the total population. And just briefly, the main causes of low hemoglobin A2 are iron deficiency anemia, which increases hemoglobin A1c, and alpha thalassemia, which decreases hemoglobin A1c. The second most common abnormality was increased hemoglobin A2. This is an example of a tracing of a patient with increased hemoglobin A2. This was much less common, occurred only in 15 or 0.6% of the population, so it was only 1/10 as common as decreased A2. And the main causes of increased hemoglobin A2 are beta thalassemia, megaloblastic anemia due to B12 or folate deficiency, hypothyroidism, and antiretroviral therapy. And these conditions change the hemoglobin A1c. So it's important to identify these people because the hemoglobin A1c does not indicate what the average glucose concentration is. So the conclusions of the study, that in this patient population, the prevalence of hemoglobin abnormalities is 8%. All these abnormalities were identified by capillary electrophoresis, and obviously none was detected by immunoassay. And the added medical value is that these 187 individuals identified should receive special attention from clinicians, and clearly the hemoglobin A1c concentration may not reflect the average glucose. So, what happens if the hemoglobin variant does not alter red cell lifespan? So there was an important question that we asked. Is the extent of glycation of the beta chain of a variant hemoglobin, for example, hemoglobin S, the same as that of hemoglobin A? Now, this is obviously an important question. And so, to answer this, we performed a study where we measured by mass spectrometry the extent of glycation of the beta chain of hemoglobin S and compared it to glycation of hemoglobin A. And this shows an example of a mass spectrum of hemoglobin AS. You can see the alpha chain, which is not important for the purposes of this discussion. There's the beta chain of A, and here's the beta chain of S, very nicely separated. And then you can see all the glycated species, glycated beta S, glycated beta A. And so what we did was we quantified these, and that's shown in the next slide here for 41 individuals, where you can see the extent of glycation of the beta chain of A in gray and the beta chain of S in black. And you can see that for most of these individuals, the beta chain of S is glycated slightly greater than that of A. And we quantified this, so the total glycated hemoglobin AS, the sickle tray individual, was 2% greater than hemoglobin AA, which would be a normal hemoglobin. So for example, if hemoglobin AA has hemoglobin A1c of 6, an individual with hemoglobin AS would be 6.1%. Now I mentioned that a change of 0.5% is deemed to be clinically significant. So it's very unlikely that this would have any clinical significance for a patient. All right, it's time to summarize. I think it's important that the clinician should be notified if a hemoglobin variant is seen, because often with heterozygous variants, neither the patient nor the doctor knows. Hemoglobin A1c can be measured accurately in the vast majority of subjects with common hemoglobin variants. And any hemoglobin variant that significantly alters red cell lifespan will alter hemoglobin A1c. And finally, if the hemoglobin A1c is less than 4, more than 15, or discordant with the clinical assessment, it should be repeated by a different hemoglobin A1c method. And finally, I would just like to acknowledge Marita Duplessis and the staff at AMPAT's National Reference Lab in South Africa for participating in this study. Thank you very much.
Well, thank you, Dr. Sachs and Dr. Higgins, for your informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you would like to ask, please do so now. Just click on the Ask a Question box located in the far left of your screen. We'll answer as many of your questions as we have time for. Let's get started. Our first question is for Dr. Higgins. Of all the factors you mentioned that affect red blood cell survival, which of the HbA1c testing methodologies used today would help identify those problematic patients experiencing these factors, and why?
Thanks, Jen, for the question. I would say that a method that can both identify the presence of hemoglobin variants and quantify the amount of variant present would be most useful in identifying people who might have altered mean red cell age. I know that HPLC and electrophoresis would work. And when I say variants, I also include A2 and F, which are not, I guess, technically variants, but identifying altered levels of hemoglobin A2, as Dr. Sachs described, might help identify iron deficiency and thalassemia trait. And identifying altered levels of fetal hemoglobin might help identify, for instance, people with altered erythropoiesis. Thanks.
Thank you, Dr. Higgins. Our next question is for you, Dr. Sachs. As chairman of the NGSP, what kinds of HbA1c questions do you get asked from clinicians?
The most common question I get from clinicians, and I get this from clinicians all over the world, both when I give presentations or in emails, is I have a patient, so the clinician says, I have a patient and the hemoglobin A1c concentration is not consistent with the clinical situation and the glucose measurement. What are the possible explanations?
And what would you say to those clinicians who ask that question?
So the approach that I suggest is the first thing would be to measure hemoglobin A1c by a different method to make sure that if there's an interference in the hemoglobin A1c, it's not specific for a certain method. And if the result is still the same, then one would suggest that the clinician looks for a hemoglobin variant, which can be done by hemoglobin electrophoresis or capillary electrophoresis. And also it's possible to look at long-term glucose concentration that's independent of hemoglobin and red cells by looking at glycation of albumin, and this can be done either by measuring glycated albumin itself or by fructosamine, which has been used for many years. So that's the approach I suggest.
Perfect. Thank you, Dr. Sachs. And another question for Dr. Higgins. What prompted you to go down the road to investigate the differences between HbA1c and estimated average glucose? And why is this important?
By the observation I'd say my initial interest was driven by the observation that there's a lot of non-glycemic variation in A1c. And we initially just wanted to quantify the effect of red blood cell age variation, and we were surprised to discover that it seemed to be explaining quite a large fraction of the non-glycemic variation. And I'd say it's important, first of all, to understand this source of variation, the interpretation of A1c as a marker of average glucose, and hopefully at some point we'll be able to use this understanding to improve the A1c based estimates of average glucose as well.
Thank you, Dr. Higgins. We have another question for Dr. Sachs. Now that the NGSP has standardized HbA1c across vendors, what do you see are the next big hurdles for the NGSP and patient care?
Well, standardization is only part of the issue. This requires obviously ongoing monitoring and working with manufacturers. But in addition, as was clearly indicated in Dr. Higgins' talk, both from the complications trial, which showed a small change in hemoglobin A1c can result in a big change in complications, and also the effect of change in red cell age, is the accuracy. So accuracy is critical. So the goal is to reduce CV as much as possible, and in addition, to try to minimize bias.
Thank you, Dr. Sachs. And we've got some other questions coming in. I believe this is for Dr. Higgins, but feel free, either of you, to answer. Okay. Okay, I'm sorry, I had some technical issues. Can you hear me? I will repeat the question. Dr. Higgins, how is mean RBC determined today?
Way to determine there's no easy and accurate way to determine mean red cell age today. The gold standard methods involve collecting blood from an individual and labeling the cells, reinfusing them, and then collecting follow-up samples every so often. It's very time-intensive and expensive, and the accuracy is a bit unclear. So unfortunately, there's currently no good way to measure the mean red cell age. I am hopeful that if we can calibrate this method basically using glucose as a label and A1c as a readout of the concentration of the label, I'm hopeful that will, if calibrated, provide an easy and accurate estimate of mean red cell age.
Thank you, Dr. Higgins. The next question we have, is there any evidence of high A1c that may not be linked to diabetes?
Yeah, that's a good question as well. And there certainly are some circumstances where individuals can have very long mean red cell age, so long, in fact, that the A1c can reach above the 6.5% level. And in that case, those people would be might be told that they have diabetes or pre-diabetes if a little bit lower, and in fact, it could entirely be a result of altered red cell age. And in those cases, having an independent measurement of glucose directly would be quite helpful.
I'll also add that there are causes of increased glucose that are actually termed secondary diabetes. So in essence, any increased glucose is termed diabetes, but these are not what one would typically think of as diabetes. So, for example, certain hormonal conditions like Cushing's disease with very, very high steroids, cortisol, or even a patient who takes high-dose steroids for several weeks to months can increase hemoglobin A1c.
Thank you, both of you. It looks like we have time for one more question. This one is it's got a few parts to it. What is the variability in RBC lifespan over time, and wouldn't CGM be needed periodically to adjust the model? Also, what is the advantage of HbA1c over CGM, considering the variables for red cell lifespan isn't constant? And the last part, do you foresee the CGM will be incorporated into the screening/monitoring methods for diabetes in the future?
So I can start. I think a number of interesting and important questions there. So first, as far as the variability of RBC lifespan, I'll say we don't know with confidence what that really is because, as I said, RBC age and lifespan are difficult to measure. I will say that using the method I described, we do have some evidence that at least in healthy people and in people with well-controlled chronic illness, it does seem to be stable, meaning that we've estimated mean red cell age in individuals, and up to two or 3 years later, it seems to be fairly stable. Of course, that would not hold for anyone with an acute illness or more serious condition. And then as for the question about whether continuous glucose monitoring should be used, instead of A1c, I guess, I think the benefit of A1c as a non-fasting one-time blood test is huge. And for a screening situation, I don't think we'll ever use CGM, which would require monitoring somebody for at least a day, if not multiple days. I do think in the future that CGM could be incorporated as maybe a follow-up test if the A1c is indeterminate or confusing. Then CGM could be used in some situations to help resolve discrepancies.
Thank you so much.
I can just add. Okay, I just want to add a quick comment that CGM does have several limitations, particularly cost. Some countries in the world find hemoglobin A1c even expensive. So CGM is much more expensive. It requires a very large, it's labor intensive. Patient has to insert a needle under the skin. And so there are lots of issues with CGM. It's not just drawing a blood sample and then getting a result.
Thank you, Dr. Sachs and Dr. Higgins. Do you have any final comments for our audience today?
So I'll just say that I think the accuracy of the A1c assays, as I mentioned in my presentation, that is going to continue to be really important, and I think the NGSP has done a terrific job driving improvement in assay accuracy. That's exciting for a number of reasons for patients and physicians.
And I'll also mention that as I indicated in one of my slides, hemoglobin A1c has become such an important component of management of diabetes that and there's a huge body of literature justifying its use and its role in complications and their targets for treatment. I don't anticipate that hemoglobin A1c will disappear in the very near future, and there doesn't appear to be any easily measurable marker that's likely to appear in the near future that will supplant hemoglobin A1c. Thanks.
Well, thank you again to our speakers, Dr. David Sachs and Dr. John Higgins, for your time today and for your important research. We would also like to thank LabRoots and our sponsor, Sebia, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today and those submitted during the on-demand period will be addressed by the speakers via the contact information you provided at the time of registration. This webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye.